data bits that are not associated with an I/O module data type. This is roughly page 7980 or so in your manual. I have the screen set where we left off with the last lab. I have you put the controller into the remote program mode, as you can see up here. And then we start discussing programs and task subroutines. In this particular case, what was created for you in the way of data containers and structure was it automatically created a task, the main task, within the main task, the main program, within the main program, the main routine with a program tag database. That's automatically created for you when you create a new project. And we've discussed some of this before, but we'll go over it again. Main task is one of a possible 32 task folders. Now that possible 32 varies with the processor. Not all of the processors that use the Logix engine can have 32 tasks. So this folder right here, I'll right click on it and go to Properties. We're online, so it's a little slower. So we go to Configuration, and you can see that it is configured as a continuous task. It could be a periodic or event task. Now there's also a motion task, but you don't create motion task at this location in RSLogix 5000. So continuous task is a task that attempts to execute continuously. Now it's going to be interrupted a little bit for certain background activities, but basically it's continuous. When nothing else is going on, this task is continually executing. A periodic task is a task that executes on a period that you define. So if you tell it to execute every 1 second, 1,000 milliseconds, every 10 seconds, every 10 minutes, that's exactly what it does. It goes for that period of time, then it executes once. Waits for that period again, executes again. This is apropos for certain things like temperature control. If you have a system where the temperature of the tank or the vessel cannot change more than a fraction of a degree in 5 or 10 seconds, why execute the code 1,000 times a second when there can't possibly be a change for the execution to work with? And then of course an event task is an event, an unscheduled event, but it's something that you're looking for, and if that occurs, then you execute that task folder once for that event. It could be a mouse click on the HMI. That could be the event that triggers that execution. Very, very handy for working with process control, working with recipes. Okay, we're going to leave it continuous and cancel. We have a continuous task. Remember, you can have up to 32 task folders, but only one of them continuous. Inside of each task folder, you can have 100 program folders. Inside of a program folder is going to be a program tag database and an unlimited number of routines, of which only one of them is the main routine. In this case, it's called the main routine, and it is the main routine. But the naming it the main routine doesn't make it the main routine. You'll find that out. So the upshot of this is a MicroLogix controller, a Select 500 controller, a PLC5 controller has one program and one tag database, if you want to call it a tag database. It wasn't called that back then, but it is the same thing as a tag database. And those tags are universal to the entire controller and to the one and only program. With the Logix engine, and we'll just take the situation where you can have 32 tasks, and each task can have 100 programs. That is a total of 3,200 programs. And each of those 3,200 programs is totally isolated from the other 3199. Each of them has their own program tag database. You could use the exact same tag name in all 3200 programs and they would not interfere with each other. Now what does set that apart is notice that your I/O is always in the controller tags. Now we put these tags IN 0 through 5 and out 0 through 3. We put that in the controller tag database simply because we're treating that as our I/O. Look at it this way. Controller tags, all I/O module defined tags are going to be in the controller tags. You can't put them in the program tags, but you can have tags in the program tag database for each of those possible 3200 programs that individually address alias controller tags, I/O tags. And in the manual, I had you change the name of the task to jumping jacks, rules of the game, and the name of the routine, whose turn is it? Just to emphasize the point that these names are not cast in concrete. It's good to leave the main program named the main program to reduce confusion. It's good to leave the main routine named main routine to reduce the confusion. Okay, next we had you go to the program tags. Whenever you see this symbol up here in scope, it shows what looks like a processor. You're in the controller tags. Okay, you can always click here and go to programs. Now we've only got one program, so there's nothing to pick from but the main program. You could just as easily, we'll close this, you could just as easily from the controller tags gone to the program tags by double clicking on the program tags. Remember that this X up here, the little gray one, not the big red one that closes the whole thing, but that gets rid of all the screens that are stacked up on top of each other. So I'll go to the program tags. You see there's nothing in there. And we are in the monitor tags. You want to go to the edit tags. Also, I believe that I said to go offline. I had you put the program in the remote program mode. We discussed tasks, programs, routines, and I see in the manual I did not tell you to actually go to the offline mode. It just says all input switches off, change any bits that are currently 1 to 0, save your program and put your processor into the remote program mode. We'll do it exactly the way I said it in the manual. That way there will be no confusion here. I had you go to the main program tags and then click on the edit tags, and you have an open field here. And in this empty field I had you type in my first bit. You could use underscores as readable delimiters. In other words, it could have been my underscore first underscore bit. However, I tend to use uppercase and lowercase to act as reading delimiters. Makes it easy to read, saves memory, saves space. This type of tag, by default, all Logix engine processors are going to come up with DENT for the data type, the default data type. And the DENT is the most efficient data type for the Logix engine. If everything was programmed with DENTs, the program would run smoother, faster, everything would work better. However, a few booleans aren't going to hurt anything. You've got plenty of memory and plenty of bandwidth. So I had you click over here. Remember, if you click here, the ellipse pops up. Notice that I clicked off of there and now it's grayed out. You can't change it. If you make the mistake of clicking outside of the data type, it creates that tag. This is if you're online. It creates the tag and you're done. You cannot redefine that tag without going offline, changing it, and then downloading. But there is another way out of this if you haven't used it in a program. Select it, hit delete, and it will let you delete it because it's not used in a program, and then start over. My first bit. Okay, then you go here and click in there and type in a B for Boolean, and there's your bool. Hit enter, the tag is created. So we just created your first bit. Then there's another bit my second bit, and I would say tags. I call them bits, but they're tags. You can go over here, and if you wanted to do it the long way, click there, and you could browse for the tag data type that you want. We want a Boolean. There it is right there. That's a lot more work than just typing in a B and hitting enter. Now watch what happens. See, right now I can still change this, but if I click outside of there, it's done. It's a tag, it's defined. You're not going to change it online. You'd have to save, go offline, change it, save, and download. I just showed you how to delete a tag. You just select it and hit delete. And as long as it's not been used in a program, you can delete it. That doesn't mean you can't delete it offline using a program, but then you're going to have rungs that are going to have E's around them showing that they're in the edit mode because they're no longer completely defined. As long as we're here, we might as well play. Let's say we want more than one tag. Select one, then you can hold down the control key and hit another. You could also hold down your key and drag it down to select more than one. So let's try something. Let's go Control C, which would copy, and then go to the controller tags, double click, go to edit tags, and go down here and do Control V. See, it won't let you do it. Back to the program tags. Try that again. Control C. It looks like it's doing something. Controller tags, edit tags, pick the empty field, Control V. Or right click, see there's no paste. Online, you're somewhat limited. It will not allow you to just indiscriminately move tags around. We'll close the controller tags and go back to the program tags. And we want to go back to the edit tags. That's where we were at. If I were to go offline, then I could do this. I could copy these tags or cut and paste them from one tag database into another. I had you save the project as, well, we'll just do that. Save as. Now I have a whole bunch of things in here. So see, I've aliased IO. I'm going to go down and put in what I told you, and that was program tags. And hit save. And then switch your tag display over to monitor tags. And you're already in the remote program mode. So my first bit, I had you type in from your keyboard a 1. And did the processor accept the value of 1? Yes, it did. Switch the processor to remote run. So you can see we're in a remote run here. And then it said, did the state of my first bit stay the same? Yes, it did. Why? Well, there's nothing to change it. You can change it from the keyboard. Logic could change it, except there's no logic to change it. Repeat the processor with my second bit. This is the same process with my second bit. See, and if we go to program mode, back to run mode, see, it has no effect on those bits because there is no program in there, there's no logic that writes to those bits. Leave both bits on for the next slab sequence. Both bits are on. Other than a different name that points to a different bit location in memory, they are both Boolean data types and identical in all aspects except the location and the pointer name. With the Logix engine and its memory, you really don't know what address, what memory location is being used that you're addressing. You are simply using a tag or a pointer that points to the actual memory location, which was assigned in the process of downloading, compiling, etc. We had you save your project and tag values. Now go offline with your project. Go offline, open the main routine. We could leave this open or we can just close it. Really doesn't matter. Open the main routine. You do that by expanding the main task, expand the program, double click on the main routine. and naturally it's empty, so it automatically creates an empty rung for you. Okay, we now want to add an instruction. There's already a rung there, so we want to add an instruction. So depending on whether or not you have the default graphical user interface up here that has this toolbar for instructions. If you don't, you can always go to View, whoops, fat fingered that, View, Toolbars, Restore Factory Toolbar Layout. Okay, it didn't change anything for me because I already had that open. I'm going to take and put my mouse over this instruction. See, when you mouse over, it gives you some explanation. Examine off, examine on. So I'm going to put my mouse over that, hold down the left mouse button and drag it. This green thing here, I call that a Mimi. Now there's only one on the whole, in the whole workspace. The fact that it's going pick me, me, it means nothing. But later on, you'll see that as you add more and more onto the screen, if you drag something down, you're going to have Mimis popping up all over the place. And there are different kinds of Mimis. This is an instruction Mimi, a rung instruction Mimi. So if that's green anywhere, see? It's not green, not green. Now it's green. I can drop it and it's going to pop right in there. Then I had you mouse over an OTE. I'll put energize and put the mouse over it, pull it down. Now how many Mimis do you have? You have 2. Now you might think that because it turns green that that's okay. Let's drop it here, even though I didn't have you do that in the manual. Let me let go of it there when that one's green. See where it puts it? That's not going to work out for us. So I'm going to grab it, pull it away. Now how many Mimis do I have? Well, that instruction's not really there because I'm actually dragging it. This is where we wanted to put it. Anyway, I'm going to delete that and do that over like we did. So you see that green Mimi there? As long as you see that green Mimi, you can let go, and that's where it will attach. But because this is a read-only type instruction here, and this is an execute or an action instruction, the action instructions are always going to go all the way to the right, whereas the read type instructions are going to go all the way to the left. That question mark there means that it wants a tag name. We'll just select that to bring the focus on it. We could go over here, see, and put the focus on that one. We'll put it on this one though. That's what we did in the manual. And then I had you double click. We could drop down the list, or we can just type in M and write it the way it comes up. You have 2 tags that begin with an M, my first bit and my second bit. Well, it just so happens F comes before S. In this type forward result, that's the bit we want. We just hit enter and there it is. Then we go over here to this question mark, highlight it or bring it into focus. We can do the same thing. M, Y, we don't want my first bit. Type an S, my second bit, hit enter. Now you could have also drilled down. We'll delete that, get it back to a question mark. I could come over here, double click, drop down the list, double click on my second bit, same result. Well, my friend, you have created your first rung of logic with your first 2 tags. You really didn't create the module defined tags. They were created for you and added when you added the IO module. Now the IN00 through IN05, OUTs through OU through 03, you did create those. But technically, these are your first 2 tags that you created and your first rung of logic. Did you notice that they were both highlighted? What is your best guess as to why the instructions are highlighted? Well, we're offline, not online. We're going to go online now. We're going to download communications, active, download. See, there could be a little confusion whether you're in the online mode or the offline mode when you're doing these labs. In this case, we need it to be in the online mode. Download, waiting. Now this is with RS-232 38.4 baud rate, so it is relatively slow compared to Ethernet. But we're using an L31 processor that does not have Ethernet. I am assuming that most people that use these manuals and watch these videos will have the least expensive processor they can get just for the sake of learning. That's an L31. Evidently, those 2 bits did not get maintained at a value of 1. So I'm going to make them 1. Remember, in our last little sequence, these were both 1. Now we'll go back to our logic, and you can see they're both highlighted. And of course, I've answered the question that I asked in the manual: what is your best guess as to why the instructions are highlighted? Your best guess and your answer is that both of these memory locations are set to 1. So even though whatever mode we're in, it wouldn't matter. If I go to the program mode, see, they're still highlighted because those bits, the state of those bits in memory are 1. And since we have nothing to change yet, because this logic does not change that, if this is true, then that's going to be turned on. Now, if I toggle this off, this is no longer true, but that's on. That's because the logic is not executing. Now, if I put this, watch this bit over here, my second bit, if I go to the run mode, that my second bit will go off. As soon as the program executes, this is false, so it turns that bit off. If I toggle this on for a true if on instruction, that immediately turns that on. When you look at this logic, everything on the left side, logic instructions, are either true or false based on the state of the memory location that they address. They are never on or off. These instructions are never on or off. The bits can be on or off, but the instructions over here, they're always true or false. Output type instructions, actions, are either on or off, never true or false, and they are on or off based on the state of the memory word or bit that they address. They are never true or false. In the manual, we emphasize that. If you don't understand this at this point, you need to go back and redo the earlier sections of this lab manual until you have this down pat. I realize that I am recording this in high definition. However, I am looking at a 27-inch high-def monitor. For your sake, I'm going to operate the geezer button. This is for the geezers. If you're 40 or over, you're a geezer. If you're 60 or over, you're an old geezer. If you're 80 or older, you're a super geezer. And Lord willing, if you make it to 100, you're an ultra geezer. Now, a geezer, I think that is 2 uses of that word. The British do something different with it, but it's similar. And a geezer in the Old West was a cowboy still riding horses and roping cows 40 or over. The young cowboys told the girls those were geezers and you needed to stay away from them. So it's not a derogatory term. Nonetheless, the geezer button right here. Make it bigger, 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 make it bigger. So we'll just leave it bigger like that for right now, because I realize you're looking at this. If you're looking at this on your, if your small tablet or your Note 4 like I have, it shows up okay, but you're going to need glasses if you're going to do this whole thing on your smartphone. We geezered up so you could see a little bit easier. Next thing I had you do was to add something called the watch table. If you go up here to view, where you saw toolbars, go down here to watch, and it pops up a little panel down here that will display any tags that you have in the ladder view. It will display them in the database. See my first bit, my second bit. Sometimes this is helpful if you have multiple rungs up here or complex rungs. You can look at the tag values down below. While watching the rung of logic, change this bit, my second bit, to 0. Now remember, you're in the run mode, remote run mode. You're executing this logic. If this is true, turn that bit on. I'm going to go down here to my second bit, select it, highlight it, put in a 0, and hit enter. We probably didn't see anything change. And if it did, it was for microseconds. If you go up here to my second bit, right click, toggle bit, it toggles it off, but guess what? It toggles it right back on within microseconds. So how fast is this program executing? We'll just jump ahead here. You don't need to know this right now, but you go to main program, go all the way down to properties, go to monitor, and we'll just reset the max here. And we'll see that the maximum execution time for this rung of logic, this program, is basically 200 microseconds, but typically it's 18 to 20 microseconds. So every 20 microseconds, I'll cancel this. If I toggle this bit, within 20 microseconds or less, it's going to turn it right back to on because this rung of logic is true. In the book, I said, did the controller's memory accept the value of 0? Well, again, you could say yes or no. I would just say no because you couldn't see it. Did the tag remain at 0? No. Why? Because the program is executing every 20 microseconds, and although you have access to the database from your keyboard, the program is quicker than the keyboard. Did this action affect the state of my first bit? Absolutely not, because my first bit is a bit whose value can only be changed by you toggling it on or off or changing it directly in the data table. It has nothing to do with whether it's in the run mode or program mode, whatever that bit is, it is. There's no execution of logic that's executing against the state of that bit. Switch the controller to the remote program mode, repeat the previous steps. Well, we can use the key switch, or we can just go to program mode. And if we go down here and put in 0, and the question is, of course, did the controller's memory accept the value of 0? Yes, it did. Did it remain at 0? Yes, it did. Why? You change the state of that bit from the keyboard when the processor is in the program mode. In the program mode, it does not execute the logic. So this rung of logic that you see right here is not being executed. So it doesn't matter whether this bit is on or off, this instruction is true or false, it has no effect on that bit because the logic is not running. Switch the controller to remote run while you're watching this rung and or this bit down here. So we can do it up here just as easy as hitting the key switch. And of course you see instantly that bit goes on. And remember that this is a graphical representation with icons with something called ladder logic, which only exists offline. There's no ladder logic in the controller. This is just a graphical representation for us. This representation down here, the state of those two memory locations, mirrors this. It's one and the same thing. Did the tag value remain at 0? No. Why? Because we went into the run mode. It executed this rung of logic and set it to 1. While watching the rung of logic change my first bit to 0. So now we're working with the other end. Now you see a different result. Did the tag value remain at 0? Yes, it did. Why? Because your keyboard is the only source that has any influence on the state of that bit. There's no I/O hooked up to it. It's just whatever you punch in directly to the database from your keyboard. Did this action affect the state of my second bit? Yes, it did. Why? Because when you turn this bit off, this instruction went false. The false execution for an OTE is to set this bit to the off state. With my first bit set to 1, which it is not right now, and my second bit set to 0, you'd have to be in the remote program mode to do that. So we'll go back to the remote program mode, which is what I had you do in the manual. With my first bit set to 1 and my second bit set to 0, which is what you see right here, 1 and 0, switch the processor to the run mode. It doesn't hurt to see this a couple times. Did my second bit remain at 0? No. Why? Because the processor immediately through the logic overwrote the state of that bit. Now we go to the remote program mode again, with my second bit set to 1 and my first bit set to 0. So actually, let's go back and put this in the remote run mode and then do that. We'll set this to 0. Remember, you can do it here, or you could have toggled that bit. Okay, now it wants my second bit set to 1. Well, we can't do that in the run mode, so we have to be in the program mode because it overwrites it as fast as we do it. So now that we're in the program mode, we'll set that to 1. Did my second bit value remain at 1? Yes, because we're in the program mode. Summary. In the run mode or program modes, the input module defined tags are updated with the current state of the input circuitry connected to the screw terminals of the input modules. In the program mode, the output module's field control circuitry attached to the screw terminals of the output module do not reflect the current state of the bits of memory that do control the state of the output circuitry in the run mode. So in the program mode, the state of those bits does not reflect this into the screw terminals to turn output devices on or off. A bit in memory is a bit in memory. Other than the name of the pointer that points to that location of memory for use in programming, they are all the same. A bit is a bit. It's just a square foot of real estate. Any bit in memory that is set by logic will have its state dominated by that logic, and anything done from your keyboard, although accepted, will be quickly overwritten by the logic if the controller is in the run mode. In the program mode, the logic is not executed and does not influence the state of the bits addressed by the output or action type instructions. All bits in memory can be read from and written to. There are 3 things in play here. 1, whether the controller is executing the logic or not, program mode versus run modes. Number 2, the state of the field side of the input points. And number 3, the state of the bits in memory that are assigned to output points. Memory locations assigned to input points always reflect the state of the input devices if the controller is powered up and you are connected and looking at it with RSLogix 5000. Whereas the output points do not reflect the state of the bits in memory assigned to them in the program mode, but they do reflect the state of those bits in memory in the run mode.